Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gill Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gill@eapen.info. My guest today is Professor Marc Pinsonneault, who is a theorist on the structure and evolution of stars at Ohio State University. His research interests range from the microphysics of stellar models, including composition, energy, and angular momentum transport mechanisms, to the observed properties of stars. An element of his current research is the use of astroseismological data from the Kepler space mission in combination with APOGEE and other spectroscopic surveys to obtain novel constraints on stellar physics, stellar populations, and the chemical evolution of the Milky Way. Welcome, Marc.
Welcome. Thank you very much for inviting me on.
Sure, yeah. So I want to start with one of your little bit earlier papers entitled Red Giant Masses and Ages Derived from Carbon and Nitrogen Abundances. Before we get into it, so you say we show the masses of red giant stars can be well predicted from their photospheric carbon and nitrogen abundances in conjunction with their spectroscopic stellar labels. Mm-hmm. Before we get to the details of it, Marc, could you set the context for what a red giant star is?
Oh, sure. The basic idea here is that if you're trying to study things like the Milky Way galaxy, you'd like to be able to look at stars that are very bright so that you can see them a long ways away, and you'd like to look at stars where you can figure out, say, how old they are, which lets you build up a kind of a history to reconstruct how our galaxy got built, where the chemical elements came from, and various other important topics for astrophysical research. Yeah. Red giant branch stars are ideal for some of these purposes because they are intrinsically very, very luminous. What happens is when a star like the sun runs out of its nuclear fuel at the center, it's currently burning hydrogen into helium. It undergoes a structural change to become what we would call a red giant branch star. It swells up, its core gets very much hotter, and it becomes much, much larger. In the distant future, the sun will become such a star, and it will eventually almost engulf the Earth, actually. It'll become so big.
So the size of that sun at that point, I think it's quite a distance away, right? 4 billion. So, yeah. But when it does that, the diameter of that star would be almost as big as Earth's orbit.
Yes. So red giants can be absolutely enormous. The largest red giants, we call them supergiants actually, would actually fill up all the way to the orbit of Jupiter in the solar system. So
the Betelgeuse is one such thing?
Yes, correct.
Yeah, okay. Yeah, I can't even imagine an entity of that size. I mean, it's just enormous.
Yeah. So these are big stars, and therefore, as you can imagine, they're really, really bright, and that makes them great, searchlights for looking across the galaxy because you can see them very far away, even without an enormous telescope. Right? So that's why red giants are interesting targets.
Okay. And so the idea here in the paper is that we can figure out their age by sort of measuring how much carbon and nitrogen is in there.
Yes, correct.
And so what's the mechanism there? So what's the mechanism that makes a star sort of balloon up like that?
Okay, yeah. The idea is that in the very center, you basically burned all of your hydrogen. You just have a pile of helium in the center, mostly. And this helium requires a much, much hotter temperature to burn than the hydrogen does. And so when a star like the sun runs out of fuel in the middle, it has the equivalent of basically a giant ash pile in the center. There's a heap of stuff that can't burn. And so the only thing it can do, therefore, is just sort of sit there. It ends up contracting and heating up. And it keeps on heating up until it reaches a high enough temperature to ignite the helium to burn heavier elements. Okay? And this requires a temperature of about 100 million degrees Kelvin, whereas the sun has a central temperature of 15.6 million degrees Kelvin. So it has to heat up a great deal. So the core has to contract.
Yeah.
The core becomes very, very hot at the edge. And because it's becoming very, very hot at the edge where there is still fuel, things start burning very, very quickly there, and it becomes extremely bright. And because it's very, very bright in the core, it's putting out a ton of energy. It also must necessarily become large. It has to grow to be able to carry out that tremendous amount of heat. And that's kind of a nutshell for why red giants are so huge and why they're so bright.
Okay, so what's the next step there? So I would imagine it's going through a progression of steps, right? So hydrogen to helium is the initial step, and then you go from helium to lithium or something like that?
The next step would be helium, and it turns out that the lithium, beryllium, boron, the next three logical elements, are much easier to destroy than they are to make, so they don't turn out to be produced. The next thing you make is carbon.
Okay.
And so you end up basically taking helium and you make a lot of carbon and oxygen.
Yeah.
And once you're doing that, making the carbon and oxygen, then eventually when you ran out of helium, you would make heavier things, but that would require even hotter temperatures. And it would require you to have an even larger core. And it turns out that for stars like the sun, they never will be able to get hot enough to do that. And so as a result, helium burning is basically the end of the line. The sun will eventually burn helium in the middle. It'll turn a lot of it into carbon and oxygen. And then the outer layers will drift off into space, and you'll end up with what we call a white dwarf star. So that's the basic picture. So you have something then that would be like most of the mass of the sun, the size of the Earth. Actually, white dwarfs are small and very dense, and almost pure, carbon and oxygen.
So the white dwarf, the formation of that is a function of the initial size and mass of the star, right? So if the star is bigger than the sun, that ends up in a neutron star or something like that? Or okay.
If it's it turns out you have to be about 8 times more massive than the sun to develop a core that is basically hot enough to be able to burn anything heavier than helium.
Okay.
Yes.
What would be the size of the white dwarf? I know that this is not the paper. I just want to get a feel for. So at that point, how big will the white dwarf be in terms of the diameter of that?
The white dwarf would be about the size of the Earth.
Yeah.
And one interesting fact is the cores of red giants are actually very, very much like little white dwarfs. Actually, it's a ball of pure helium. It doesn't have any nuclear reactions going on. It's super dense and super small. And then you ignite helium, it puffs up, and then after you run out of helium, it shrinks back down, and that's the size of the star.
But it's still producing some, it is still doing some nuclear reaction, right? It's still producing some energy?
The energy in the core of the white dwarf is only from gravitational contraction. It's not actually doing any nuclear burning. The nuclear burning occurs on the edge of the core where there's still hydrogen and it's very, very hot.
Okay.
So that's So your physical picture is you have this tiny, super dense little core in a red giant. A material on the edge of this core is being burned, it's being deposited as ash, and the core is getting smaller and smaller and smaller, and hotter and hotter and hotter. And then the envelope is popping and very expanding dramatically. It's developing like this enormous contrast.
Right.
And then after you've ignited helium, you turn helium into carbon and oxygen. And then the star basically experiences a lot of what we call mass loss. The outer layers are lost due to a series of instabilities. The outer layers become kind of unstable. And then at the very end, you're just left with the dense little ball in the center, which then becomes a white dwarf.
So what would be the surface temperature at that stage of the white dwarf?
When it is first born, the surface temperature would be like incredibly hot, almost 100 million degrees. It's almost as hot as the temperature you need to burn helium, but it cools very, very, very quickly. And the oldest white dwarfs have temperatures at the surface that are kind of similar to that of the sun or cooler, some few thousand degrees.
Okay.
Most observed white dwarfs have temperatures of sort of tens of thousands to thousands of degrees.
Thousands of degrees. So they will never become sort of habitable, right? It will still be reasonably hot.
And crushing gravity, because all the mass of the sun packed into a volume the size of the Earth.
Right.
And so as a result, you can imagine that if you ever tried to, say, stand on one, quite apart from the thousands of degrees temperature, you'd be squished like a bug, right? I mean, it would just be incredibly intense conditions.
Okay. And so since we know this progression reasonably well, the idea here is that you can measure the carbon and nitrogen in a red giant, and that gives us some indication of the age of the star.
Yes, and the basic idea. To step back a little bit, one of the problems with red giants is that although they're very, very bright, stars with a wide range of ages end up being funneled to looking in most ways very similar at the surface. So in other words, I can have a star that is 1 billion years old and a star that is 10 billion years old, and they will both become red giants, but they'll become red giants with, say, temperatures and gravities and things that are very similar to one another. I mean, there are subtle differences, but those subtle differences are very, very hard to pick out. And so we have this paradox that you have these stars that are tremendously bright, but they look very much alike one another. So it's very hard to use that as a way of tracing out, say, ages. And so what we're trying to do, where this space data has been amazing, is it gives us a key for decoding basically what the true ages of stars are, to look for the right clues that tell us that some of these are very relatively young. For an astronomer, 1 billion years is young, and some of them are very, very old. 10 billion years is almost as old as the universe. So that's the game.
Yeah, go ahead.
And so what we're trying to do is we're trying to figure out ways we can clues we can use. And one of these clues has to do with the fact that when these giants become so incredibly, incredibly huge, they have a mixed region on the outside, like the surface of the sun. It's boiling. And this boiling of the surface of the sun really ends up basically mixing the outer layers very, very thoroughly. And so since these giants are so big, they get mixed much deeper, and they mix deep enough to actually be able to dredge up or pull up processed material from deep inside their core. Okay? And because because stars that are very high mass are very hot in the center, they have a lot more nuclear processing. And so high mass stars will therefore have much more processed cores. And that means that you can actually see that they'll dredge up a lot more heavy things when they become giants than a star like the sun would. Now, the last piece of the logical connection here is high mass stars basically burn bright and die young. right? And so as a result, the linkage is high mass, short-lived, lots of nuclear processing that shows up at the surface. And that means whenever we see a lot of nuclear processing, we kind of know that's a pretty young star. It's a high mass star that didn't live very long. And whenever we look and we see there's very little of this processing going on, we know that it's a star that had a pretty cold core, and that means it lived a long time.
So you looked at a large number of red giants, so about 1,500 red giants. So the estimation of age and mass that we are deriving from this data, is that consistent with what we expect to see?
The age estimates that we got were reasonable, but the real trick was knowing what the ground truth was in order to be able to do the work, and that's where this field of seismology is really comes in.
So that's the second paper there is spectroscopic determination of masses and implied ages for red giants.
Yeah.
So there you're saying from Kepler and APOGEE surveys, samples of several thousand stars exist with high quality spectra and astroseismic masses. So what is astroseismic process?
Yeah. This is one of these things where basically we have there's been a fascinating explosion. It's one of the ways in which all this space astronomy has completely changed how we think about things. And the idea for astroseismology is that I told you that stars like the sun are kind of boiling at the surface. You can imagine there's all this turbulence, right? And when you have basically all this turbulence, you create, sound waves, right? And these sound waves are going to be bouncing around inside of the star. Just like they would be anywhere else. And if you have a wave with the right wavelength, what can happen is the wave is bent or refracted as it goes into a star like the sun because there's such a huge contrast in density. Okay? So what that means is you can imagine I have some wave, it starts going down, but the material it's going into is denser and denser and denser. And so the wave starts bending and eventually it reflects and it bounces back. Now, if you basically go all the way around the star and you have exactly the right bending angle, you're going to come back to the place where you started. And then in that case, you have a standing wave. Okay. So in this case, what can happen is I'm rattling around. I have all of this turbulence just generating all these things. And every once in a while, things line up just so that you create a standing wave pattern at the surface. And what that would mean, therefore, is there would be nodes or places where basically all the material would be going up, and then it would be getting colder. It would look faint. And there's other places where it's all going down, and it would be getting hotter, and it would look bright. Right? So if you wanted a simple picture of one of these waves, the simplest mode you can imagine is like water sloshing in a pan. Right? So like water sloshing in a pan, one side goes up, one side goes down. Right? So that would be kind of one of the modes you could see, and that would correspond to half of the star getting bright and the other half of the star getting dark, and then it reverses, right?
So this is observable in even optical range.
Yes. And so what happens is if you basically have very sensitive instruments, and our telescopes in space are very, very sensitive, then what happens is these even small variations in brightness have a regular kind of frequency pattern that you can come out. So it's going to be oscillating because this wave is going to go around and it's going to ring, and I'm going to see basically that it's oscillating with some characteristic frequency. Now this isn't like a pure sound because, of course, there are many, many of these modes that it's possible to excite in stars. So the sun, we've identified more than 100,000 individual modes of oscillation, right? Because the sun is an oboe; it's not a flute.
Can we simulate actually how it might? There is no sound in space, but how it might sound like?
Yes, in some cases you can visualize it because some objects, as we've talked about, white dwarfs. It turns out that if you actually, white dwarfs actually oscillate at a frequency that would be audible to the human ear. The stars like the sun are unfortunately a little bit out of that range, so you wouldn't be able to hear the sun, if you will. But some stars do oscillate in the audible frequency.
Right.
But so the idea isn't that we're hearing, the sound waves directly. They're not traveling through empty space to get to us. What we're doing is we're seeing the star varying in brightness as the material in the star moves back and forth, responding to these waves.
Right. And so this gives us an indication of the mass of that particular star.
Yeah. And the way that works is that the frequency of these sound waves depends upon the sound speed, which depends on the density, right? So you have in some sense, if you're measuring these frequencies, they tell you something about the mean density of the star, which goes as mass over the radius cubed. And there's a second feature I talked about, which is that basically, remember, I told you that you had to have waves bouncing up and down in the star. They start at the top, they go down, they come back up, they go back down. And for them to reflect at the boundary, there's also another critical frequency they have where they can't basically have a frequency that is too high. If the frequency is too high, they won't be able to bounce back up and down. And it turns out that criteria, that second ingredient, depends on the surface gravity of the star, which is m over r squared. And so one thing you can do is you can ask, what range of frequencies do we see? That turns out to tell you what the gravity of the star is. And the second thing is basically, what is the detailed pattern, which frequencies we're seeing? Those differences, we call those frequency differences between the modes, tells us about the density. So we have one thing that goes as m over r squared, one thing that goes as m over r cubed, and we can solve for m and r. That's basically what we do.
And this technique is only useful in a red giant context, right? Because things are moving around. Lot more than a typical star. We can use the same technique on a star, right?
Well, they're useful for any cool star. So we do see them in the sun, and we see them in giants. But the problem for stars like the sun is the amplitudes are absolutely tiny, and the frequencies are high. Whereas giants, because their densities are really low, the frequencies are much lower, and the amplitudes turn out to be much higher. And so it's a fascinating kind of like almost an accident that it turns out that red giants oscillate with frequencies like 30 minutes, an hour, a day, a week, a month. It's those kind of frequencies. And we put up all these satellites to look for transits, to look for Earths, which basically take images of the sky every 30 minutes, which is absolutely perfect for red giants. And so, and so it's just an accident, really, that it turned out that people said, well, if you want to look for an Earth around another star, you basically know that takes about 2 hours for the Earth to transit the sun as observed from space. And you need 4 points to get a measurement, so you need to sample every 30 minutes. That's what they do, right? And turned out that if you were saying, let me design a machine to measure oscillations in red giants, you would have said sample every 30 minutes.
Wow. Yeah. So the transit method, as you say, is to identify the planets. And so, if I understand this correctly, Mark, the planets that we are interested in and the distance they might be from their sun, the observations seem to very accidentally coincide with sort of the 30-minute looks into that. And so that the same sort of data allows us to identify red giants too. Is that the idea?
Yeah. And so you use exactly the same data. I mean, the space satellites are just taking movies of stars every 30 minutes, looking for the little blip when the brightness drops, when the Earth-like planet passes in front of the star. And you take exactly the same data, no changes, and you then analyze it, and you see these oscillations. You see this rattling around these sound waves as another signal in the stars.
Is there any possibility of some sort of cross error? If they are sort of vibrating in the same 30-minute intervals, is there any possibility of picking up some errors in the transit
Yeah,
method?
yes. In fact, it does actually make it harder to find planets around giants because you have to remove this signal. But there is a difference. The difference is, for example, that if you look carefully at like the shape of the curve, there's a very distinctive signal from eclipses that's different from oscillations. But you're right that you actually have to be careful. There's many false backgrounds that you have to remove for this. There's actually a lot of data analysis.
Right. Mark, we'll take a quick break. When we come back, we'll talk about giant stars in the solar neighborhood.
Okay.
Talk to you soon. This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com. So we are back. So Mark, we've been talking about red giants, what they are, how to measure their size, mass, and so on using data that has been collected by Kepler and other missions. You have a recent paper entitled "Young Alpha-Enriched Giant Stars in the Solar Neighborhood."
Mm-hmm.
So what is alpha-enriched stars?
Okay. The sun has a certain mix of elements that span the entire periodic table. And we know that virtually all of them, all the elements heavier than lithium, were basically made in stars to first order, right? So they all were manufactured sometime over the history of the galaxy. And there's lots of sources, but there are two sources that are really important. One of these is the explosions of massive stars. When stars that are much more massive than the sun, they build up cores that go all the way up to iron. They then explode. And when they do, they produce a lot of the elements on the periodic table. And in particular, a lot of ones that involve like oxygen and neon and magnesium and silicon. And each of these is built by basically capturing a helium nucleus or an alpha particle on top of the previous one in the chain. So you make oxygen by combining carbon and helium. You make neon by combining oxygen and helium, and so on. And so we call all of these things alpha capture elements. Okay, and then they're one of the things that you make the most of in the explosions of very massive stars.
Which that's what's called supernovae.
Yeah, supernovae. So supernova type 2s. We call them supernova type 2s. We have this really arcane language, all these subclasses of stars. They get super baroque. It gets super complicated. but this is a type 2 supernova. Okay. And the other thing that can happen, and the thing about this is that these are very short-lived stars. And so these alpha capture elements got made starting almost right away when we made stars. They can start happening after only a few million years after the first stars are born. Now, the other thing that can happen is if you wait a lot longer, you can have a much lower mass star that makes a white dwarf, a different kind of remnant. And if you dump mass on top of a white dwarf, you can actually kind of detonate it if the conditions are right.
Yeah.
And if you detonate it, what can happen is you can actually have an explosion where you destroy the entire star and you basically turn it into almost pure iron or iron peak, elements very close to iron. Okay? Now, these explosions, because they make a ton of iron, the massive stars make a ton of these alpha capture elements, and the sun kind of is an average of all of these. So the sun has kind of an average mixture of these two pieces. But if you look at the very oldest stars, there wasn't time to have these white dwarf explosions. And so they have a lot of these alpha-rich elements. So we call these basically, a lot of these alpha capture elements. And so we call these things alpha-rich because they have a lot of, silicon or magnesium, relatively little iron. Okay, so that's what alpha-rich means.
Okay. So iron is iron sort of the end of the line there in terms of making these elements? So to get iron, I guess you have to have a supernovae, right?
Yeah. You have to have one or the other of these things. And the white dwarf explosions are called supernova 1As. They're just different kinds of supernova explosions.
Okay.
And the reason is they're classified by their appearance, how bright they become, how quickly they dim, things like that, and less about what their actual origin is. And so the idea is that that's where the elements come from, but these two different sources take different amounts of time to turn on. Okay. And so to first order, I would expect that if I was looking at stars that were made before these white dwarfs happened, they would have a lot of alpha elements, very little iron. If they were looking at afterwards, they'd have an equal mix. Now there are elements heavier than iron, but they're made through a different process, but they're actually quite uncommon. That's why we call them things like rare earths, right? They're made in stars, but they're made through other processes, and the absolute numbers of them are small.
So Mark, just a quick. So my voice, I'm getting a feedback from your side. Could you reduce your volume a little bit? Not your volume, but my volume on your side.
Okay, is this better?
Yeah. That's perfect. Yeah. So just give me a few seconds. And so there is a distinction between what you call alpha elements. So they are like oxygen, magnesium, silicon, and so on. Yeah. And then there is iron that is produced in a sort of a different process. Yeah. And the rare earth and heavier elements are produced by other types of processes. So the composition of a star actually tells us a lot about sort of the origin of that star. Is that the idea?
Yeah. And stars in different environments might very well have very different mixes. Yeah. And so if you let's say, for example, our Milky Way galaxy made stars at a certain rate, okay, and the sun has the mixture that it does. But we know that there are other galaxies where they made all their stars much, much more quickly, right?
Yeah.
And in systems like that, maybe all of the stars, including stars like the sun, would have a lot less iron relative to all the other elements, right? Because they made all their stars at once. And there might be other galaxies. A good example of this is the satellite galaxy of our Milky Way, the Magellanic Clouds. And these are small galaxies that took a very long time to get around to making a lot of stars, right? And so then in that case, there would be almost none of these alpha-rich stars. All of the stars would have a mixture that looked like the sun. And so when you're looking at this mix of elements, it's giving you clues about how quickly a galaxy made stars.
Yeah, so the composition actually tells us sort of the history of the galaxy in some sense, right?
Exactly.
Yeah, not only the age, but sort of the activity, the intensity of star formation, and how the galaxy sort of grew up, so to speak.
Yes. And so this is a big reason why we're now undertaking a lot of surveys from the ground, where we're measuring the composition of very large numbers of stars using kind of automated tools. And that it's largely because we'd like to be able to use it as a diagnostic tool to reconstruct the history, the formation history.
Right.
And this is...
Yeah, go ahead.
And this mix of elements is one of the big clues we use to tell us what that history was.
Yeah, so I was just thinking, Mark, since you're going to get a lot of labeled information here from Kepler data and other missions, this is an area potentially some machine learning could help us as well, I would think, right?
Oh yeah. In fact, that's an absolutely essential tool for this. Yeah. Because the issue that you have is that the spectra that you're looking at, in other words, you basically take the light, you pass it through the equivalent of a grating or a prism, you spread it out, and you look for features to identify in the spectrum. And what you're trying to do then is you're using this to kind of map out what the abundance is. And then what you're trying to do is you're saying there's a small subset of stars where I really know what the age is.
Yeah.
But I can't apply these complicated, astroseismology tools to all the stars in the galaxy because I can only do those tools directly for a very, very small number of objects. Right. So I have a small set, it's significant. It's tens of thousands or tens of thousands of stars, but it's not millions of stars. I have a sample of, let's say thousands of stars where I have very, very good information about their ages. And then I have a sample of 1 million stars where I don't have all that information.
Right.
But there's a piece of it, there's something they have in common. I'm able to take a spectrum of both of them where I can look at the strength of various features and I can figure out what they're made of. And so the machine learning tools are the things you can then use to say, is there any feature in that spectrum that I can use to predict the age?
Right.
And that's what we've been trying to do with machine learning.
Yeah, I mean, it's really exciting. So I would imagine in the future, if you get those models right, in future missions, we could actually key in the characteristics of a star, such as age, mass, brightness, whatever you have, and then let the machine go find a star precisely with those metrics, right? From the spectra, it can actually identify something.
Yeah.
And it might have some implications for, obviously hunting for life. There is hunting for planets, habitable zones, and so forth. A big part of that is finding the right star too, right, in a neighborhood that is reasonably calm. And so I wonder if it will have some applicability there as well.
You could use it. You could imagine using that to basically see, are there any characteristics in common, say, between systems that have Earth-like planets and ones that don't, right? And you could use it to train it in that way to look for good targeting. So the technique has a lot of promise. Machine learning, of course, in this context, of course, also has a lot of challenges. One of the difficulties is confusing causation and correlation. And so, as a trivial example, I told you that you make heavy elements in stars, and that means that on average, you need more generations of stars to make a star with a lot of iron than one that has very little iron. Right. And so that means if you run a machine learning algorithm through and say, what's an age diagnostic? It'll say, well, the iron abundance. The more iron you have, the older you are. Except the point is that that's actually a relationship that has a tremendous amount of scatter in real stars. It's not terribly predictive.
It's also a function of, if I understand this correctly, Mark, it's also a function of how much violence existed, right? So if you got a ton of supernovae going on, it might have created a lot of iron in that process.
Yeah, exactly. So it's a clock that's very unreliable in some sense. But the machine learning might just key in on that, and then it'll basically say, well, all stars with a lot of iron are relatively young, right? I'm sorry, I misspoke. The stars with a lot of iron would be relatively young, and stars with little iron would be very, very old. And so it would just completely tangle this. And so you have to be able to be careful to make sure that you're using, diagnostics that the features that it's pulling out are actually physically tied to something reasonable. Right. And that's one of the reasons why we talked about this carbon and nitrogen abundances, because we actually think there's a physical reason why the mixing in the star ought to be tied to the age.
Yeah, so it's definitely a problem. I'll call it blind machine learning. And it's sort of going on in other industries, Mark, as you know, in healthcare, for example, we use a lot of machine learning, and it is really a projection of history. So if you have lot of noise in history, you could end up with conclusions that actually don't make any sense, or even exactly opposite to reality, right? So, like you say, it has to be some sort of a collaboration between human and machines to actually
Yes.
make it usable.
Yes. Yes.
I want to jump into another, a more recent paper entitled Dynamical Heating Across the Milky Way Disk using APOGEE and Gaia data. So you say the kinematics of the Milky Way disk is a function of age, are well measured at the solar radius, but have not been studied over a wider range of galactocentric radii. So dynamical heating across the Milky Way. So what is dynamical heating?
Okay, so the idea here is that we live in a spiral galaxy, and so what that means is that our galaxy, or much of it, as seen from space, would actually be quite flat. And so a spiral galaxy is one that has a very large disk, very, very flat. It can have a bulge in the middle of older stars.
Yeah.
And there are other galaxies called, for example, ellipticals, where there is only the ball. There's only a kind of a spheroid or something in the center, and there's no disk at all. And so what we think happens here is when the Milky Way galaxy was born, it was spinning, and of course, as things contract, they conserve their angular momentum, and like a figure skater, she pulls her arms in and she pulls her arms in. She spins faster and faster and faster. And eventually what this means is it's easier to collapse in one dimension than the others, and you end up with kind of a disk of gas that's left there spinning. And this disk of gas that's left there spinning can then eventually form stars that will remember where they came from. They'll actually be spinning around in a disk. And the gas in our Milky Way galaxy is in a very thin layer. It's very cold. And that means that you would expect the Milky Way galaxy, stars in the Milky Way galaxy, to be born almost exactly in the midplane of the disk. That's where the gas and dust is.
Right.
Okay.
And so the gas, the stars we see in the edges today, on the edges of Milky Way, are they old stars, or are they created in the middle and then migrated to the edges?
And that's the business, is that the Milky Way is a fascinating and complicated place precisely because stars move from where they're born. And they move in two different directions. One way they can move is radially. They can move in and out.
Yeah.
And this can happen because, for example, there are spiral arms in the galaxy, and there's a bar in the center of the galaxy. And these things can actually kind of make stars kind of just move in and out quite dramatically. We call this radial migration. Okay. And the second thing that can happen, which is where the dynamical heating is relevant, is you can gradually, through a series of encounters over time, kind of kick a star up or down so it's no longer orbiting exactly in the middle of the disk, right? And so that means that if I look at the Milky Way galaxy, I do see a very thin disk of young stars.
Yeah.
And if I look at older stars, the disk is substantially puffier or larger than that, right? And so how you get from A to B is this dynamical heating business. It's also true that there are some models where when the galaxy was very, very young, the disk was kind of hot and puffy.
Yeah.
And over time, the disk has cooled down. And so then in that case, the old stars are far away from the middle of the disk because they were born there, because the disk used to be a lot fatter than it is today, right? So disentangling these two histories, where stars basically all born flat and then they puffed up, or were they born in a puffy disk that cooled, distinguishing between those two scenarios is a big question in dynamics.
So they are sort of mutually exclusive mechanisms. Ultimately, we'll figure out what the mechanism might be, or it's a combination.
It could be a combination of the two, and that's why we really have to have very good data to be able to distinguish one from another.
Okay.
We know that both can happen. We know that, of course, as stars get older, they can only get, quote, heated because they will just by chance encounter other stars or spiral arms or giant clouds of gas that will perturb their orbits. And these things can only go one way. They can only make you puff up.
So we know that there is a supermassive black hole at the center of the Milky Way. Does it have any effect on this process?
It certainly has an effect very close to the center. Once you get far away from the center, it looks to a star like the sun like any other 3 million solar mass group of things.
Yeah.
They can have a big impact on the local environment. They can also have a dramatic impact on the ability of a galaxy to make new stars. Because if the black hole at the center swallows too much gas, becomes too bright, it can actually put out so much light that it disrupts the gas clouds that form stars in the rest of the galaxy. It can actually shut off star formation.
So from what we observed today, Mark, am I correct in thinking that the supermassive black hole we have in Milky Way is sort of silent? In other words,
it's relatively quiet compared to some other galaxies. And one thing to note is that most galaxies, in fact, do not have extremely active black holes at the center. We believe that all galaxies probably do have massive black holes, but we don't. But most of those black holes grew in the distant past. They swallowed all the stuff near them, and they're not growing anymore. Right? And so that's very similar to our own Milky Way galaxy.
Yeah. So the star formation disk, I like to think that in sort of a nursery for stars, right? That disk is sort of living independently from the black hole today, right? In Milky Way, it is just creating stars without a lot of influence from the black hole.
Except in the very, very center, where there is a cluster of young stars near the very center, and the orbits of those stars are very strongly perturbed by the black hole. In fact, that's actually how we detected the black hole, is we can look at it as its gravitational influence on the stars that are very close to it.
Yeah, we recently had a sort of a picture of the Event Horizon, right? Is it called the Event Horizon Telescope?
Yes. And there are Nobel Prize properly awarded to the people who discovered and characterized the central black hole. So that's been amazing.
Yeah, that's an amazing thing because it was a theoretical construct, right, about 100 years ago. And we came all the way experimentally to actually take a picture of something you can see, which is an incredible engineering accomplishment, I think.
Oh yeah. And just being able to prove that it's there, right? Through kind of classical measurements, the orbits of stars is actually great work.
Yeah. And so, in conclusion, Mark, I know that you're doing a lot of work in this area. Do we have other missions like Kepler in the process right now to really look at these types of things in terms of star formation and those types of things that we talk about that is really focused on that area?
Yeah. This is a topic with a fantastic future. Yeah. There's the Kepler mission, and the successor mission to Kepler, which is called TESS by NASA, is actually looking all sky, and it could be going for a very long time. And so as a result, Kepler was staring very intensely at one small patch of sky in the constellation Cygnus for about 4 years. And TESS is scanning the entire sky every 2 years. It looks at the northern hemisphere, flips, looks at the southern hemisphere, and repeats. And there's a space mission called Plato, which the European Space Agency is going to be putting out. It'll be launched in 6 or 7 years. Yeah. And when Plato launches again, it'll give us another terrific trove of data. So these space missions are ongoing and, in fact, expanding. We are anticipating that we could have hundreds of thousands of these astroseismic detections in TESS and comparable numbers in Plato. So this is a subject that's only going to grow as we continue to study it. It's a fantastic time to do astrophysics.
Yeah, a lot of data to come in. So both from a theoretical perspective as well as from an engineering machine learning perspective, this is going to be really rich in the next 10 years or so.
Yes, absolutely.
Yeah. Excellent, Mark. This has been great. Thanks so much for spending time with me. And
okay, great. Thank you.
Good luck with this research.
Oh, yes. Absolutely.
Thank you.
Thank you.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.